The world is full of contradictions. One doctor says a treatment is safe, another says it's not. One law declares something legal, another calls it illegal. One historian frames an event as progress, another as tragedy. We all live in these tensions, and what we need most isn't a single final answer, but a way to understand why the answers differ. The missing context that makes both perspectives make sense. Yet when we turn to today's AI systems for help, they don't know how to handle this. Instead of clarifying, they collapse into the answer you happen to prompt them with, or smooth over the conflict with polished but shallow prose. In doing so, they make the contradictions harder to see, not easier. That's the problem we're tackling today. Our project is about teaching AI to treat contradiction not as failure, but as a signal of missing context. We're giving models a new reasoning habit, to see that when two claims clash, they often do so because of a moderator, time, place, role, scope, or definition, that explains how both can be true. By aligning models with triadic reasoning patterns, we enable them to preserve multiple truths, partition conflicts responsibly, and explain their choices out loud. Instead of hedging vaguely or refusing bluntly, a triadic model says, under condition 1, this is true, under condition 2, that is true. The result is a system that is not only fluent, but resilient, auditable, context-aware, and safer by design. Large language models, LLMs, have transformed how machines interact with text, but their limitations are becoming equally clear. When faced with contradictions, overlapping contexts, or shifting definitions, current models often flounder, either collapsing prematurely into one answer, hedging vaguely, or producing smooth but unstable reasoning. These behaviors stem from a deeper structural issue, a default mode of reasoning rooted in binary and pairwise patterns. Here we propose a new cognitive habit for LLMs, triadic pattern alignment. Rather than treating statements as isolated pairs, such as claim versus counterclaim or question versus answer, this approach teaches models to recognize and reason through triads, structured relations among three interdependent elements. In this logic, contradictions are not flaws, but signals of missing context, and that context often takes the form of a moderator, for example, time, place, definition, role, or scope, that reconciles conflicting claims. By aligning model behavior with a structured set of triadic patterns, such as coexistence, reinforcement, harmonic balance, exclusivity, and more, the system becomes capable of holding multiple truths conditionally, resolving apparent paradoxes, and tracing reasoning paths that remain coherent across contexts. We call this project pandemology, a practical path to embedding triadic reasoning in LLMs without requiring changes to model architecture. By incorporating triadic logical patterns and training on triadic examples, LLMs can reason through contradiction instead of avoiding it. By making this approach more scalable, we move closer to public AI models that don't just produce fluent responses but think contextually, resolve conflict, and explain reasoning. All traits essential for high-stakes decision-making, nuanced conversation, and trustworthy systems. Classical and dialectical logic, whether in formal systems, political theory, or philosophical discourse, have long sought to resolve contradiction through synthesis. A claim is opposed by its counterclaim, and these opposites are presumed to resolve into a higher-order conclusion. This prescriptive habit forms the backbone of dialectical reasoning: thesis, antithesis, synthesis. But dialectic contains a foundational fallacy, one that becomes especially problematic for systems like LLMs. It presumes that contradiction must always be overcome by generating a new truth. Yet logic is not inherently prescriptive. Logic, at its best, is descriptive. It maps how ideas relate, how truths condition one another, and how context shapes coherence. It does not demand resolution, it exposes structure. In practice, contradictions don't always resolve. They often reveal missing context. When a system tries to collapse opposites into synthesis without locating the frame that justifies both, it commits the same error dialectical systems do. It confuses surface disagreement for structural incompatibility. This project begins from a different premise. Meaning is structured triadically, not dialectically. Concepts don't exist as binary oppositions, but as triadic interactions among interdependent elements. Two positions, A and B, may appear to contradict, but their relationship is often conditional on a third variable, C, the moderator. That moderator might be a time, a place, a role, a definition, or a scope. In this view, contradiction becomes a signal, not of failure, but of missing information. Where dialectic asks which of these is true, triadic logic asks under what condition are both true. In triadic reasoning, truth values are informational, whether positive or negative. The presence or absence of a trait, A or not A, is not just a verdict. It reveals the system's structure, the relationships in play, and how the overall state might shift under transformation. Both affirmation and negation serve as data about inclusion, exclusion, dependency, and transition. Large language models, though powerful, remain vulnerable to dialectical failure. They collapse too quickly into a single answer, hedge vaguely when faced with contradiction, or smooth over conflict with language that feels coherent but lacks structural integrity. These limitations trace back to a deeper issue, a pairwise reasoning habit that lacks the dimensionality needed for contextual resolution. We propose a new cognitive habit for LLM's triadic pattern alignment. Rather than structuring reasoning through binaries, question versus answer, claim versus counterclaim, we teach models to reason in structured triads. That means identifying pairs of interrelated claims and the moderator that conditions them, classifying their relationship through a formal triadic pattern, such as coexistence, reinforcement, harmonic, or exclusivity, and reasoning accordingly. This proposal outlines a method for embedding triadic logic in LLMs without requiring architectural changes. Through fine-tuning on formal triadic examples, annotation of real-world text with moderators, orchestration layers that ensure consistency, and behavioral evaluation metrics, we aim to create systems that reason through contradiction rather than avoid it, and that make their reasoning transparent by explicitly stating the moderator and triadic pattern applied. In doing so, we build models that are not just fluent, but contextually aware, structurally coherent, and capable of reasoning across contradiction with clarity and accountability. This shift is not just technical, it is epistemological. It moves LLMs closer to the kind of reasoning that humans struggle to master, one that preserves plurality by locating structure rather than erasing difference. Modern LLMs are often described in reductive terms, as systems that predict the next token based on the last. But this view misses the deeper nature of their architecture. These models do not merely chain words together, rather they operate across the entire input context, embedding and retrieving high-dimensional patterns that span multiple layers of abstraction. Each layer in a large transformer model processes more than just surface forms. It builds internal representations that capture syntactic relations, the structure of how words fit together grammatically, semantic patterns, the associations between meanings and categories, and latent logical tendencies, implicit rules of inference, contradiction, and constraint. While LLMs have developed strong intuitions for syntax and semantics, because they are well represented in natural language corpora, they remain underdeveloped in logic. Not because the models are incapable, but because the training data and objectives have not emphasized explicit, reusable, interpretable logic structures. This is where triadic logic enters. Our triadic patterns provide the missing layer, a formally valid, composable logic framework that aligns naturally with the architecture's existing strengths. These patterns do not need to be hard-coded. They can be taught as reusable cognitive habits. Once internalized, they act as templates for integrating, aligning, and generating relational structures across contexts, just as syntax and semantics currently guide composition. From this perspective, we are not adding something foreign to the model, we are completing it. We are supplying a third dimension of reasoning that gives coherence and constraint to otherwise fluent but unstable outputs. Triadic reasoning structures information through three-way relations: a claim A, a counter or complement B, and a contextual moderator C that determines how A and B relate. These triads form a kind of logic grammar, a set of structural patterns such as coexistence, reinforcement, dissonance, or exclusion. Each provides a reusable scaffolding for understanding contradiction, dependency, and transformation. By aligning model behavior with these triadic families, we teach it to recognize contradictions not as problems to avoid, but as signals of incomplete context, contexts that can be resolved by identifying the correct moderator. For instance, if one source says X is legal and another says X is illegal, the model can learn to resolve the contradiction by looking for C, like jurisdiction, time period, or definition, and then correctly partitioning the claim. Importantly, LLMs are uniquely suited to this training. Their architecture is already structured to detect and reproduce complex patterns. By introducing formal triadic templates, both abstract and real-world examples, we simply extend the space of recognized relations from syntax and semantics to logic. Once learned, these triads propagate through the model's layers like any other learned structure, informing generation, guiding reasoning, and providing a framework for conditional coherence. This approach also mirrors how humans build concepts. We rarely hold truths in isolation. We understand them through contrast, through perspective, through context. That structure is not binary but triadic. A belief is justified not just by its opposite, but by the frame that makes the belief coherent. Teaching this structure to LLMs means teaching them to think more like humans, not just in language, but in logic. At the core of this project lies a formal but intuitive insight. Certain triadic structures appear again and again in natural reasoning. These patterns, when recognized and named, provide stable scaffolds for interpreting contradiction, mapping causality, and tracing inference chains through complex contexts. Each pattern represents a different form of conditional coherence, a way in which three related elements, A, B, and C, sustain a balanced structure by mutual implication, dependency, or resonance. In this section, we walk through the 11 affirmative triadic families. Each one encodes a logic that the model must learn to identify, apply, and explain. By training on these as distinct classes of relational reasoning, the model gains not just more expressive power, but a grammar for assembling truth conditionally, and explaining why things hold together the way they do. In the coexistence pattern, the elements are mutually reinforcing and interchangeable under the same condition. Each one implies the others. And honestly, none can be truly separated from the rest without dissolving the whole triad. If A holds, then B and C must also hold, but if any of them fails, the others do too. Think of body, mind, and environment in holistic medicine, or inalienable rights in political philosophy. You remove one, and the others just unravel. The model must recognize that in such triads, truth is a mutual presence, and contradiction arises only if one part is affirmed or denied independently. Reinforcement is basically a positive feedback loop. Each element strengthens the next in a continuous cycle. So, A leads to B, B to C, and C loops back to support A. This is really the structure of resilience and self-amplification. For example, in teamwork, trust leads to communication, communication builds coordination, and coordination reinforces trust. When the model sees this pattern, it learns that the presence of any one element strengthens the whole, and the absence of any one can weaken the loop. It's a dynamic pattern, thriving on continuity and return. Causal is a more linear and constrained form of triadic reasoning. A causes B, B causes C, and crucially, if A does not occur, C will not either. This allows the model to trace inference paths forward and backward while maintaining logical dependency. Unlike reinforcement, which cycles, causal triads unfold along a path, and breaking the chain at any point dissolves the conclusion. This pattern is ideal for structured processes. Policy leads to implementation, which leads to outcome, or hypothesis leads to experiment, which leads to conclusion. The model learns that causality isn't just a sequence. It's a conditional scaffold with, honestly, pretty fragile links. Nonlinear triads work through indirection. A leads to C, which in turn leads to B. The way this is experienced is often that without the first event, the second event could not occur, but the second event's significance is not realized or relevant until after a third event. This structure is common in policy design, systems thinking, and complex problem solving where the outcome is mediated. For example, education policy, that's A, may affect economic growth, that's B, through improvements in workforce capability, which is C. The model must infer that some effects are mediated and that reasoning paths may arc or fork without being broken. This pattern enables more nuanced conclusions than direct causality allows. The inclusive pattern builds hierarchical nesting. A leads to B, B leads to C, and C consolidates both A and B. This is how foundational elements accumulate into higher-order concepts. For instance, curiosity, that's A, leads to exploration, that's B, which leads to learning, that's C, and learning is defined by both prior curiosity and exploration. It's also common in developmental logic, where each stage incorporates the one before. The model learns to recognize integration upward. The end state is not just a result, but a synthesis of what preceded it. In conjoined triads, B exists only if both A and C exist. This represents joint necessity. Neither A nor C is sufficient alone, but their combination gives rise to B. It's a logic of and, not or. Think of engine function, which is B, requiring both fuel, that's A, and ignition, that's C, or trust, which is B, requiring both transparency, that's A, and consistency, that's C. The model learns to reason in converging dependencies, where a missing element breaks the whole. This pattern enables safe planning, diagnostics, and synthesis. The harmonic triad is the purest mutual balance. Any two elements generate the third. It's a logic of resonance and reconstruction, like musical harmony, where any pair of notes implies the chord. Applied to ideas, empathy emerges from both attention and presence. Presence can be inferred from empathy and attention, and so on. The model must grasp that the state is overdetermined. Each element exists not independently, but as a function of mutual reinforcement. It's one of the most human-feeling patterns, ideal for understanding moral reasoning, creativity, and emergent properties. In the convergent triad, each element implies the co-presence of the other two. It's a logic of minimum completeness. No single piece stands alone. Each is a window into the whole. This pattern is useful when truth must be triangulated. A test is only meaningful if conditions B and C are satisfied. Or in storytelling, character implies conflict and setting. The model learns that partial information is suspect, and that confidence increases only when multiple conditions co-occur. In the combination pattern, the presence of any two elements prevents the absence of the third. If A and B come together, then C cannot be missing. If B and C align, A cannot be missing. And if C and A align, B cannot be missing. The dynamic here is not that two factors directly create the third, but that they block its absence. The triad locks itself into wholeness. Whenever a pair exists, it forces the full set to appear, while the absence of anyone prevents the other two from coexisting. It is a structure of completion by exclusion, where every pairing implicitly guards against incompleteness. For example, consider a fire safety system. If both heat and smoke are present, then the alarm cannot be absent, it must sound. But if the alarm is absent, then you cannot have both heat and smoke at once. One of them must be missing. The system enforces all or nothing completeness. Whenever a pair arises, the full set is compelled into being. In the association pattern, one element, B, acts as a hub. If B pairs with A, then C cannot be missing. If B pairs with C, then A cannot be missing. And if A and C attempt to stand alone without B, the logic of the pattern immediately pulls B into the picture. This creates a system in which no pair can stably exist without the third completing it. The special role of B is that it cannot tolerate being in a partial coalition. Whenever B forms a partnership, it requires the triad to close. Meanwhile, A and C cannot form a stable bond without recruiting B. The result is a strongly associative structure, where all paths lead to the completion of the full set. For instance, imagine a workplace project where B is the manager, A is the designer, and C is the engineer. If the manager and designer collaborate, the engineer must also be present. If the manager and engineer align, the designer cannot be absent. And if the designer and engineer attempt to carry the project forward without the manager inevitably becomes involved. In association, every working pair naturally pulls the missing element into the fold. Integration is a pattern of cross-gated support. Each of the first two conditions says that one element can lead to B, but only if the other element is not absent. If A is supposed to lead to B, then C cannot be missing, otherwise the pathway fails. Likewise, if C is supposed to lead to B, then A cannot be missing, otherwise that pathway fails. In other words, each possible route to B depends on the silent cooperation of the other element. The final clause seals the picture. When both A and C are present together, B must follow. Taken as a whole, this means lone causes cannot produce the outcome in isolation. Their influence collapses if the other is absent. But when the two combine, they ensure the manifestation of B appear. Integration is not simple simultaneity. It is a system of mutually gated pathways, where effectiveness only arises through cooperative presence and progression. For example, think of medical recovery where A is proper medication, C is patient rest, and B is healing. If medication is given without rest, its pathway to healing fails. The patient does not recover. If rest is taken without medication, that pathway also fails. Each treatment depends on the other's presence to succeed, but when both medication and rest are present together, recovery is secured. Integration expresses the principle of joint gated sufficiency. Each condition relies on its partner, and only through their integration does the outcome reliably. By internalizing these 11 affirmative triadic patterns, the model acquires more than just a library of templates. It acquires a structured habit of thought. Each pattern represents a different kind of stability: feedback, containment, emergence, dependency, and each offers a reusable, interpretable way to process contradiction, assemble meaning, and extend reasoning without collapse. But these are only half the story. Each affirmative pattern also defines the dynamics of its own negation. The negated families describe the ways structures break down, how harmony becomes dissonance, how conjoined elements bottleneck when one fails, how coexistence dissolves into incoherence. These are not mere opposites. They are informative disruptions. When a negated pattern is present, the model can infer what's missing, which moderator failed, which support collapsed, which dependency broke its chain. This dual structure doubles the inferential power of the system. Every pattern not only tells the model what is, but allows it to ask what must be true if this is not. Negation becomes a diagnostic tool, not a void, but a guidepost for identifying absence, exclusion, constraint, and tension. And this, ultimately, is the deeper proposition of the project. We are not imposing an artificial logic on language. We are not writing new code into the model's architecture. We are tuning the model to perceive and reproduce the patterns already present in information itself. Human beings reason triadically all the time, often implicitly. We resolve contradictions by introducing missing context. We understand phenomena by placing them within frameworks. We navigate meaning by aligning syntax, semantics, and structure. Triadic logic is not an invention. It is a recognition of the way coherence emerges from interrelation. This proposal does not ask the model to pretend to be logical. It asks the model to see what logic actually is. Not a set of rigid rules, but a set of relational rhythms, balanced, conditional, contextual, and expandable. By training LLMs to attune to these patterns, to name them, apply them, invert them, and explain them, we transform them from language imitators into contextual reasoners. This closes our conceptual introduction to the project. What follows will show how these patterns can be practically embedded, reinforced, and evaluated, not just as abstract ideals, but as usable, internalized habits of thought. Over the past 2 years, we've been building something different from yet another dataset of question and answer pairs, a library of structured reasoning in the wild. More than 3,200 videos now live on our channel Pandemology, each with transcripts available for reuse in training. Some are straight-up analyses of formal triadic patterns: coexistence, reinforcement, exclusivity, and so on. But as you may know, many go further. We embed these patterns into stories, poetry, and narrative experiments, and we trace them through texts as varied as ancient scriptures, mystical traditions, and modern scientific papers. The point is not to limit ourselves to one domain, but to show that triadic patterns are inherent to the structure of information itself, no matter the source. For model builders, that variety is the asset. A fine-tuning dataset that blends formal reasoning with narrative, symbolic, and technical examples creates models that don't just parrot logical forms, but can recognize and apply them across contexts. Instead of brittle task-specific training, you get a substrate for generalizable conditional reasoning. Each transcript comes with meta-explanations woven into the text, making the logic behind the pattern explicit. So the model isn't just mimicking outputs, it's absorbing the reasoning grammar. If you've played with LoRa's, Hugging Face datasets, or custom fine-tunes, you know the bottleneck isn't GPUs, it's content with depth and structure. That's what this library provides: open, reusable material that can seed experiments in alignment, safety, evaluation, or creative reasoning. But this project is not only about machines. The same videos and transcripts that feed the models are also there for people, for anyone who wants to train their own mind to see the deeper structures in language, thought, and culture. Once you start looking through the triadic lens, patterns reveal themselves everywhere. In how laws differ across jurisdictions, in how myths layer meanings, in how scientific concepts evolve under shifting definitions. Watching the videos isn't just passive learning, it's practice in attunement, a way to sharpen your own reasoning by noticing the conditions that hold multiple truths together. So whether you're a developer, fine-tuning models, or a thinker curious about new habits of mind, we invite you to explore pandemology. Training loops are cheap. Training data that actually shifts reasoning, for AI or for us, is what's rare. This is our attempt to make that resource available, both for the next generation of systems and for the next generation of human reasoning. We hope you join us again.